Okay, we're looking at stretching, shrinking, and reflecting graphs in this section. First one is the vertical stretching. If you look at this graph here, we have a graph of f of x, which is right here, in black, and we have y is equal to some factor c times f of x. Here it says indicate that c is greater than 1. So if a point xy lie on the graph y is equal to f of x, this is my graph f of x. Let's take a look at the point here. This is the point x and y. Then the point xcy, which would be right here on the graph that is stretched, lies on the graph of y is equal to c of f of x. Now if this constant c is greater than 1, then the graph of y is equal to that factor c times f of x is vertical stretching of the graph of y is equal to f of x by applying a factor of c. So once again, if I have a graph y is equal to f of x, and you want to see how would be the graph of y is equal to c, some factor c times f of x is look like. If c is greater than 1, like if you have 2 times that function or 3 times that function, then the same graph of f of x would get stretched vertically like you see here. In the figure, the graph labeled y1, which is right here, is the graph of f of x, which is equal to absolute value of x. This is the graph that is not stretched. The other 3 functions, we have y2, y3, and y4, correspond to some factor times that f of x, correspond to 2 absolute value of x, 3 absolute value of x, and 4 absolute value of x, but not necessarily in that order. We want to determine the correct equation for each of these. The given value of c, the factor of c is 2, 3, and 4. The vertical height of the point with the same x coordinate of the 3 graphs will correspond to the magnitudes of these c value. While the graph just above y is equal to y1, which is the absolute value of x, will be that of y is equal to 2 absolute value of x. The highest graph will be that y is equal to 4 absolute value of x, and the graph of y is equal to 3 absolute value of x lies between those two. If a point xy lies on the graph of y is equal to f of x, so this is my graph in black, is y is equal to f of x. Then the point CCY lies on the graph of y is equal to c of f of x. If this value of c is between 0 and 1, then the graph of y is equal to c times f of x is the vertical shrinking. Remember, we were talking about stretching. If c was greater than 1, the graph would stretch. In here, if c is between 0 and 1, the graph will shrink by that factor. So in this figure here, we have y1 is equal to f of x is equal to x to the power of 3. We want to know which one of these would be 0.5 x to the power of 3, 0.3 x to the power of 3, and 0.1 x to the power of 3. As you can see, all these are going to shrink because the c is in between 0 and 1. So if you look carefully, if the c factor is between 0 and 1, so the more compressed toward the x-axis the graph will be. So in this case, since c is 0.5, 0.3, and 0.1, the function of rules must be as follows. y2 would be 0.1 x to the power of 3. So that's y2. y3, this one right there, y3 would be 0.5, and y4 would be 0.3. Would be y4 would be 0.3 times x to the power of 3. If a point xy lies on the graph on y is equal to f of x, then the point x over cy lies on the graph on y is equal to f of c of x. Now these are the two factors that you have to remember. If c is between 0 and 1, then the graph of y is equal to f of cx is a horizontal stretching of that graph, y is equal to f of x. If c is greater than 1, the graph of y is equal to f of c of x is horizontal shrinking of the graph of y is equal to f of x. So this would be a good example. So if I have y is equal to f of x times 1/2 x, the 1/2 is between 0 and 1. As you can see, that would be the case where it stretches. And in this case, c is equal to 2. It's greater than 1. It's greater than 0. So c is greater than 0, that's 2. So y is equal to f of 2x. As you can see, this case would be your graph is shrinking. That would be another example here. When c is greater than 1 or c is between 0 and 1, how the graph horizontal shrink or horizontal stretch would appear. Use the graph of y is equal to f of x to sketch the graph of y is equal to f of 1/2 x. So f of x is given to me, and these points are known. 0, 0, 2, -1, -1, and -2. These are the points given in my f of x graph. So because c is 1/2, which is between 0 and 1, so the graph of y is equal to f of 1/2 x is a horizontal stretching. So graph of y is equal to f of x can be obtained by dividing each x coordinate of the graph by factor of 1/2 or 0.5. So the point -1 and -2 that was given to me on my graph of f of x would become -1 over 0.5 -2. The point 0 and 1 turns to 0 over 0.5, and so on. The next one would be 2 over 0.5. So these are my points here: -2 and -2, 0 and 1, 4 and -1. So we can sketch. Reflecting the graph of the function across the axis. These are the points that you want to definitely write down in your summary sheet. For a function y is equal to f of x, the graph of y is equal to minus f of x is reflection of the graph across the x-axis. This would be an example of that. So if this is f of x, y is equal to minus f of x would be a reflection across the x-axis. The graph of y is equal to f of minus x is reflection of the graph f across the y-axis. So this is y is equal to f of x, and here would be y is equal to f of minus x. So you replace for each x minus x in this f function. So when applying this reflection across the axis, given the graph of the function f of x here, this is the f of x, we want to graph f of y is equal to minus f of x, and also we want to graph f of minus x. So as you can see, would be the first one would be a reflection across the x-axis. You see how this line here is reflecting across this x-axis. It goes down here. So you notice that 0.2 and 6 returns to 0.2 and minus 6, because that's a reflection of x-axis. 0.76 on this line will reflect to 0.7 and minus 6. So this line here will transfer to this line because it's reflecting across the x-axis. Look at this point here. Point -4 and 0 right there would be reflecting point x-axis, would be stay same place because it's on the x-axis. Still would be -4 and 0. Point -1 and -3 reflect that to the x-axis. That would be right above this. Becomes -1 and 3. Instead of -1 and -3 would be -1 and +3. So this graph would be the graph of y is equal to minus f of x would reflect on x-axis. The next one would reflect on the y-axis. So you notice that every point on this f of x, 0.2 and -6 would reflect to y-axis. So it would be right, mirror image of y-axis would be right here. So it would be -2 and 6. The 0.7 and 6 would reflect on y-axis, becomes -7 and 6. This 0.0 is on the y in the origin, stay in the origin. You can pick another point here, like this point here, -1 and -3. It's right in the left side of this y-axis. Reflect that to the y-axis would be right to the right of that. Mirror image of that would be right this point here, okay, which is 1 and -3. So this graph here would be a reflect of the graph of f of x on y-axis. So combination of transformations that we looked at so far. In this case, if I have y is equal to -3 times x minus 4 to the power of 2 plus 5. So this is really moving a graph of y is equal to x squared, this parabola here. We're moving this parabola here around, and let's see by what factor. This 5 indicates that this graph of parabola would shift up 5 units, if you recall. This constant here would shift the parabola up. This number here, this y is part of the formula. This 4 plus 4 indicates that the graph of parabola would shift to the right 4 units. This minus, if you recall, that would be reflection across the x-axis. So if originally the parabola opens upward, now the parabola would open downwards on the y-axis. And this factor here, 3, as you recall, that is a vertical stretch by a factor of 3. So if you look at y is equal to x minus 4, this would be the graph that shift to the right 4 units. and then this 3 would the shrinking factor. Negative would make reflect, instead of opening upward, now is opening downward. And finally we have y is equal to minus 3 times x minus 4 squared plus 5. Plus 5, we're going to shift this whole thing 5 units up. So we can do it in any order you like. As you can see, all the shifts appears. Given the equation of the function that would be obtained by shifting the graph of y is equal to absolute value of x to the left 3 units, vertical shrinking the graph by applying a factor of 2/3, reflecting across the x-axis, and shifting the graph 4 units down in order to scratch its graph. So you can see absolute value of x was originally going up. This minus would bring that going reflected going down. Minus 4 means we're shifting this 4 units down. Plus this plus 3 means that you're shifting this to the left 3 units. So you go down 4 units, 3 units to the left, and vertical shrinking the graph by applying the factor of 2/3 means multiplying 2/3 and then reflecting across the x-axis, change 2/3 to minus 2/3. And then we're going to we used all the fact to translate y is equal to absolute value of x to where the new graph is supposed to be now. Describe how the graph of y is equal to absolute value of minus x plus 1 can be obtained by transforming the graph of absolute value of x. Y is equal to absolute value of x. So the graph of y is equal to absolute value of x must be shifted to the left, because this is plus 1, this really is minus 1, so it's shifting to the left, and reflected across the y-axis. So in performing transformation, horizontal shift should be performed before reflections. The graph on the next slide, you can see that first we look at y is equal to absolute value of x plus 1. That means the horizontal shift. And as you can see, this would be shifting the graph absolute value of x to the left 1 unit. Remember, this was x minus 1, shifting to the left 1 unit. And then the graph, this graph below shows that y is equal to absolute value of x plus 1 reflected across the y-axis, resulting in y is equal to absolute value of minus x plus 1. So if you look and see what it was before, we had y is equal to absolute value of x. We shift this to the left 1 unit, so this would be y is equal to absolute value of x plus 1. So if I replace x with minus x, then this would reflect across the y-axis. So that goes right like this. From here, the blue one is reflect on y-axis, that becomes this red one. So the y is equal to absolute value of minus x plus 1. the figures shows two views of the graph of y is equal to absolute value of x. One is absolute y is equal to absolute value of x, and another graph illustrates a combination of transformations. We want to find the equation of that. Okay, so the law of things happening here. Let's take a look. The origin from 0 shift to 3 and minus 2. So let's take a look. So from 0 go all the way to 3 and minus 2. That means that you're shifting this graph to the right 3 units, and you're shifting it down 2 units. Okay. Let's see what else is happening. The point on the right side of the transformation graph has 4 and 1. This point 4 and 1 is on the final transform graph. So the slope of this line can be obtained because I know the 2 points on the line here now. 3 and minus 2, 4 and 1. I use my slope formula y2 minus y1 over x2 over x1, and you can see the slope of this line is 3, whereas the slope of the line originally was 1. So what that means is the stretch factor is 3, and the equation of the transformation now we can obtain would be 3 times absolute value of x minus 3. Again, this minus means you're shifting this to the right 3 units. This minus 2 means you're shifting that 2 units down. So that would be the equation of transform graph.